Well, let's go ahead and get started. Again, welcome to everyone who's joined us today. I'm Samantha Link, and I'll be moderating today's webinar on locating damage in the dark, pinpoint robotic localization for inspections. As we go through the presentation today, all attendees will be muted, but please be sure to send in questions through the Q&A feature located at the bottom of your Zoom webinar screen. I'll go ahead and introduce our presenter today, Thomas Keady. Thomas has been at Gecko for 2 years in the engineering department as an electrical engineer, developing and testing localization systems for robots. Thomas was a double major in electrical and computer engineering and received his master's in robotics, all from Johns Hopkins University. Alongside his localization work, Thomas also helps design many of the other TOCA series robots, electrical systems, and the robot's onboard firmware. Today, he's going to take us through the systems and controls that help with localization for identifying asset health and pinpointing critical areas. Let's all welcome Thomas.
Thanks, Sam. And hello, everyone. I'm Thomas. And as I go through this today, please do feel free to send in your questions, and I'll do my best to answer them as we go along. That way we can address your concerns and make this as relevant for you, whatever your interests are. So what we're going to go over today is what is localization and what is its purpose. We're also going to talk about why localization is different for inspection robots versus other types of robots you might see in the news. We'll go over a brief history of some technologies that have been developed to solve these problems, as well as a little more detail on some modern implementations. And then finally, we'll go over some use cases. And this is a very acronym heavy space. So I'm going to try my best to define all these terms before I start throwing acronyms at you. So here we've provided a little cheat sheet of some of the things you're going to see and hear about today. Feel free to reference this or take a screenshot. And one acronym of particular importance is year over year, which refers to the ability of different measurement systems and different operators to correlate the measurements they take over time, which is a big pain point in the industry currently. If you think about inspections taken at different times or different techniques, in order to extract the most information from them, you want to make sure they are located at the same locations on your asset in real life. This is because we use NDT technology because they can see things and measure things that humans can't, like precise wall loss or, say, backside pitting. And in order for this information to be useful when it's time for a human to go into the environment and do, say, the repair work, they want to make sure that what they're seeing is the same spot that, say, a robotic inspection method saw. And one way to solve this problem is through the concept of digital twinning, which is the idea of taking all the information that you have about your real-world asset and building a digital computer model of it, where you can do fun things you can't do in real life, like seeing through walls or accelerating time, to measure things like loss rates or erosion rates, as well as perform predictive maintenance. So one of the many things you need to do to build a digital twin is localization. And localization is the problem of determining your position in an environment, which means it's very closely related to the problem of mapping. Because in order for your localization knowledge to be of any use, you need to know something about your environment. And there are many types of maps we can build. We can build visual ones, like what humans make with our eyes. We can use NDT methods, like MFL readings or ultrasonic scans. And there are other types of maps, like magnetic field strength. But today we're going to focus on the localization problem. And if you think about the needs of many robots that you might be familiar with, like warehouse robots or self-driving cars, or these ones here from Boston Dynamics, their goal is just to get to their target destination and not hit anything along the way. They care about navigation and obstacle avoidance, which is very different from an inspection robot. At every instance that an inspection robot takes a scan, they need to know precisely where they are in the environment for that scan to be of any use, which means they need to know their position more or less continuously, which is different from these other types of robots. If you think about the case of, say, a self-driving car, it might take the same route every day along your commute, but it doesn't really care if it changes lanes, say 10 feet ahead or 10 feet behind of where it did yesterday, as long as it gets you where you're going and doesn't hit anything. And so what this means is that a lot of technologies commonly used for robot localization won't necessarily meet the requirements of robotic inspections. What this means is that our requirements are closer to the field of surveying, which is defined as the technique, profession, art, and science of measuring 3D positions and the relationship they have to each other. Now, this problem has been around for a long time. It's most commonly encountered in the field of civil engineering because for hundreds of years, humans have been building things, right? We need to build canals, roads, buildings. And in order to do that, you need to know something about your environments, often relatively large environments. And so we've come up with lots of tools to solve these problems. Originally, they were rather rudimentary, things like chains and levels. Eventually, we graduated to angle measurement devices like theodolites and sextants. And then once man-portable electronics came along, you suddenly had this wide variety of options available. You can use radio waves, lasers, ultrasonics that pass through the air. You can use more complicated systems like cameras for photogrammetry. And these systems culminated in some of the most commonly used options by civil engineers and surveyors, which are the Global Navigation Satellite System, or GNSS, as well as robotic total stations, or RTSs. And with this plethora of options available, you can imagine the thoughts going through my head when I watch my favorite sport of football still rely on literally the oldest technology in the book, the chains, to determine if someone got a first down. But I digress. We don't just borrow the technology from surveying, we also borrow some of their techniques and concepts. And one of the most important ones is the idea of a control point. A control point is a special location on your asset or in your environment that is surveyed through multiple methods and serves as a reference. The idea is when you deploy a robot in an environment, you measure its initial position relative to the closest control point. And then any subsequent measurements collected by that robot can be referenced against that control point, such that once it's time for, say, the repair crew or the plant operators to come in and see what the robot saw, they can use these control points to identify those locations. On this image on the right, you'll see one that's used by land surveyors. In the field of inspection, they can look very different. They can be existing features of the asset, or they can be leave-behinds. The important part is that they're very clearly identifiable. Another important concept we use from the field of surveying is the idea of repeatability and reproducibility. So repeatability is the ability of your system to return to the same location over a short period of time. For example, say a robot traverses a certain plate and gets a bad scan. And by bad, I mean of low quality. In order to get a quality measurement there, you want your robot to be able to drive to the same location it visited before and take another measurement. Its ability to do that is called repeatability. Reproducibility is slightly different. Reproducibility refers to the ability of other systems and other operators to correlate their measurements with measurements taken by other systems or other times. And so this again is where year over year reproducibility becomes very important. Because if you want to measure things like the degradation rate of your asset or perform predictive maintenance, you want very, very good reproducibility of, among other things, your localization data. So these are metrics that we use to evaluate and design the systems for robotic localization for inspections. So here is a brief overview of the systems we're going to talk about today. And not to worry, you can look at your acronym sheet, but we will define all of these as we go along. What you're seeing here on the x-axis is the accuracy of these systems, and on the y-axis is their range. And that yellow bounding box in the middle is roughly the requirements of robotic inspections. These are driven by the desires of our clients to have a certain amount of accuracy, and then the types of assets that they operate, which define the range. And the systems we're going to talk about today, which you see plotted here, we're talking about them because they fall roughly within these boundaries. So starting with radio-based systems. These are very popular for a lot of applications like inventory tracking people or objects as they move through indoor environments. And that's because they're cheap, they're lightweight, and they scale very well. The trouble is their accuracy generally isn't that great. It's limited to a few feet. And what this means, generally speaking, is they're not really applicable for robotic inspections. The reason we're mentioning them is because you might see numbers advertised for these types of systems that sound better than you think. And that's probably because those measurements are relying on a technique called fingerprinting. Fingerprinting is essentially measuring the baseline electrical characteristics of an environment because the signals that these radio-based technologies use are very easily disturbed by features like piping and wires in the walls, appliances like routers, and just the materials used for construction. And the trouble is that these parameters are very hard to model. The best way to determine them is to measure them empirically. And then if anything in the environment changes, say you move a piece of furniture or a repair takes place, you need to re-fingerprint the environment, which means these techniques generally are not well suited for robotic localization systems because they depend on the fingerprinting. Now, let's say you took the idea of radio-based localization and mixed in atomic clocks and the theory of relativity and just took every dial you had and cranked it up to 11. What you would get is the Global Navigation Satellite System, or GNSS. GNSS is fundamentally radio-based, but because of the complexity and the ingenuity of the system, you can achieve extraordinarily high performance localization across the entire world. And it's commonly known as GPS. The reason we're calling it GNSS here is because GPS refers to the American implementation. Since then, other countries have produced similar systems, including Russia, China, the European Union, and some other countries have regional systems. And because GNSS is fundamentally triangulation-based, the more signals you have to produce your measurement, the more accurate you'll be. And most modern receivers, like the ones you'll see on most robots or in your latest iPhone, can use signals from all of these systems at once. So what you're seeing here on the right are called sky views. And what sky views represent is, say you were laying on your back, looking straight up at the sky. The location of these satellites on the sky views corresponds to where the satellites would be in your field of view if you could see them. And what you want is what's like the image on the left, where your satellites are very spread out. That's how you get the best accuracy, is when you have a wide field of view to the sky. Now, on the other hand, say you were doing like an exterior tank shell inspection on these tanks on the right, because the tanks are so close to each other, your field of view of the sky would be rather narrow, which means your satellites would be clustered close together. And then you run into the skinny triangle problem. In this domain, it's called geometric dilution of precision, and that will really hurt your accuracy. Now, say these tanks were fixed roof and you were doing a roof inspection. In that case, GNSS might work well for you. On the other hand, if you were doing a floor inspection or you're on a boiler, GNSS will be practically useless. So what this means is that GNSS is only sufficient for a relatively narrow subset of robotic inspections. However, because it is so popular for the field of surveying, it can be used for collecting control points because it has excellent performance, excellent reproducibility because it's operating 24/7, which means it has good parameters for measurement of control points where you can use other systems for your actual inspection. Other systems like the robotic total stations I mentioned earlier. These are very commonly used by civil engineers. Their fundamental operating principle is they have a very, very high performance laser rangefinder. These things will have the accuracy of millimeters over the range of miles. So they're very impressive. And you mount one of those things on two very high resolution rotation axes, pitch and yaw. And what that means is that you sight the rangefinder at a target, measure the distance, and simultaneously measure the angles with those axes. And with some basic trigonometry, you can calculate the location of that target relative to your total station. Now, because they're robotic, these things are motorized, so they can track a moving target. Previously, before they were motorized, you would require a human to manually spin the dials to sight your target, and that would be infeasible for tracking a moving robot. However, despite their motorization, they do need a operator to handle obstructions. Anything as thin as, say, a rope or a pipe supporting a scaffold will block their rangefinder. And what that means is that once your robot drives to the other side of that obstacle and re-enters its field of view, you do need a human operator to steer it and reacquire tracking. Now, these things are really great for measurements when you have relatively few obstructions, and they're also excellent for measuring control points in the environment. The trouble is, they're so great because you're paying for it. They are extremely expensive, and they do require some training to use. Now, the next system we're going to talk about is very interesting, but before I move on, there are some images on the next slide with flashing lights. And so for people with light sensitivity considerations, this is your warning. I am moving on to LightBased Metrology, which goes by several names, but we're going to call it LightBased Metrology, or LBM. And the way this works is it converts that angle measurement problem from RTS into a time measurement problem. One of the primary drivers of RTS cost is the difficulty with designing and fabricating those precision angular measurement components. On the other hand, electronics are very good at measuring time. So the way these systems work is if you look at the image on the bottom right, you'll see a flash and then the two spinning rotors. So what happens is this is a light-based metrology base station. It emits these signals into the environment. And a light-based metrology receiver essentially measures light. And it starts counting when it sees that flash. Then, because the receiver knows how fast the rotor is spinning, it can measure the difference in time between when that sweeping plane of light intersects it and when it last saw the flash, so it can measure its angle relative to the base station. Then you have these two sweeping rotors moving in different directions. And if you have multiple receivers in a known configuration, you can calculate not only their distance relative to the base station, but also their orientation, which is a nice bonus. So if you construct this type of system properly, you can get RTS level performance plus that orientation knowledge at short ranges. And there's a few trade-offs here. So when it comes to obstruction handling, these light-based metrology systems perform better because they do it automatically. If the field of view from the receiver to the base station is obstructed, it will lose its localization knowledge. But then once it re-enters the field of view, it can automatically recalculate its position using the timing of the laser light without human intervention. Additionally, because these systems are cheaper to build than RTSs, you can deploy multiple of them in environments, meaning they can cover their shadows. If there is an area that is obscured by an obstruction from one base station, you can deploy another one to cover its range, and visibility to only one base station is sufficient for the receiver to determine its position. And these trade-offs compared to the RTS are, of course, they work at shorter ranges. Now, one thing you might have noticed about all the systems I've discussed so far are that they rely on line of sight. They require a clear view between the transmitter of the signal and the receiver in order to function. And try as we might, we can't always make this happen. Inspection sites are very complex, right? There's a lot of things going on. And so we just can't always get a line of sight. And what that means is we need to carry some sensors on board the robot such that they can never be obstructed and they're always reporting information to us. Two most common sensors used for this are wheel odometers, like what you have on your vehicles that can measure distance traversed, and additionally inertial measurement units, or IMUs. These are the things that your phone uses to tell when you've turned it on its side, or that a Segway uses to help keep itself upright. And additionally, most of them these days will also have compasses, which is useful for determining your orientation. Because these systems don't rely on line of sight, they'll always report information to us, and we can integrate them into our localization calculations through a set of techniques called sensor fusion. And the idea behind sensor fusion is that even though the information coming from a wheel odometer looks very different than that coming from, say, an IMU or an RTS, mathematically, we can combine them with knowledge of the environments and knowledge of the robotic system that's carrying them to produce the most optimal calculation of the variable we care about, which in this case is our robot's localization. And there's two main benefits to this. The first one is simply more information helping you produce better results. And the second one is that redundancy I mentioned before, which means if, say, you lose line of sight temporarily, or if one of your sensors breaks, you can fall back on your remaining set of sensors to maintain good localization knowledge throughout the inspection. You also may have been wondering why I haven't mentioned LiDAR yet, because LiDAR is very common and popular for a lot of mobile robots these days. And this is primarily because they tend to have two really nice features. One is a wide field of view, often 360 degrees at a certain fan angle, and they're carried completely on board by the robot. So they don't require any external setups. Now, this is really great for the needs of most mobile robots I was describing before. They're great for detecting objects and helping you avoid them. The problem is the performance of a single LiDAR laser measurement is not comparable to, say, an RTS. But because you have so many of them, with a little bit of computational power, you can still extract features and detect objects that you're looking at in the environment, which again is great for obstacle avoidance. The trouble is, when you use a LiDAR for localization, its performance will be entirely dependent on the type of environment you're in. For robots that navigate in human spaces, like indoors and rooms, things like furniture and doorways make great features for a LiDAR to use for localization. Similarly, outside, you'll see buildings, cars, trees. Again, these things are great for helping you localize. When you compare that to, say, the inside of a boiler or the inside of a tank, there's relatively few unique features for a LiDAR scan to bounce off of. And what this means is they're difficult to use in these environments for localization purposes. In the worst case, you can imagine an external pipe inspection or, say, a sear inspection. There may be no objects nearby for an emitted LiDAR scan to bounce off of. And so what this means is that LiDARs are only useful for localization purposes in a relatively small subset of inspections. If you compare it to an RTS, the LiDAR sort of takes a shotgun approach. It throws out hundreds of medium accuracy scans in all directions, which again is very useful for obstacle avoidance. But For localization purposes, if you compare it to an RTS, which uses just a single, very high precision laser rangefinder pointed exactly at the one thing that you care about, the localization of your robot, it's clear that the RTS will typically be a better option. So another important metric to use when evaluating the systems here is the security. As you can imagine, these systems are quite complicated. The hardware may be designed by one company, the software developed by another, and then the deployment and operation may take place by a third party. And then who knows how many communication nodes the information they generate will have to pass through before it gets to its target destination. So there are a few considerations here. Take the examples of cameras and LiDARs. You can point these devices at your assets for the purposes of inspection, but for the purposes of localization, they're more beneficial if they're outward facing in the environment. For cameras, for instance, you need distinct features for, say, computer vision or photogrammetry. And what this means is they capture a lot of information extraneous to your inspection. The camera will point at whatever happens to be nearby. It could capture operators, the people you have on site. It could capture signage. It could reveal information about logos and materials that you use. And this information has been used in the past to compromise operations. In the case of Stuxnet, for example, we don't know for sure because we don't officially know the designer of the bug, but based on forensic analysis of its code, it's believed that it used information from images released by Iranian government's PR departments to learn information about their centrifuges, the computers controlling them, and the arrangements they had. And that information helped them build Stuxnet, which severely impacted their operations. LiDARs produce similar problems. They can reveal things about the size and shape and the types of structures you have nearby. And additionally, this is just a lot of data. It can make it hard to manage. Compare that to the surveying systems we've discussed so far. The outputs of these systems of, say, GPS, robotic total stations, or light-based metrology, they simply generate coordinates of the item you're tracking, which in this case is your robotic inspection. And that information is a lot harder to use to exploit to disrupt your operations. Additionally, because it is so focused, it is a lot smaller volume of data to handle. Now, there are still differences between these systems. For instance, the architectural similarity of GNSS and light-based metrology means that the information generated is more private. If you think about the perspective of a GPS satellite, it has no knowledge of who, if anybody, is localizing with its information. It's just throwing these signals out into the environment, and a receiver who knows the right protocol can decode them to determine its location. This is also true for light-based metrology. A light-based metrology receiver doesn't need to communicate with any central authority or any other receiver in the environment in order to determine its location, which also means that it can make the decision about who to share its information with. In the case of a robot performing an inspection, it can use its calculated location to timestamp the measurements and their position, and then send that data off to the customer. So if you compare this to a robotic total station, the total station carries the rangefinder and also carries the rotation axes. So the information it generates is at the station. In fact, a robot or anything being tracked by a total station may not even be aware that a total station is tracking it. So these are additional considerations that can be useful for evaluation and choosing which type of system you'd like to use for your inspection. And now we can move on to the fun part, which are the use cases. So let's take the case of a non-confined space entry tank floor inspection. An RTS is very suitable for this type of application because generally the insides of tanks have relatively few obstructions. And additionally, you can deploy an RTS either inside the tank manway or just outside of it. And this will give it a great field of view to the inside of the tank. Additionally, because robotic total stations are so precise, they can give you the small bin size and high resolution that you want in your NDT inspections that take place on tank floors. Now, additionally, there is a little bit of icing on the cake when you use an RTS. Recall that robotic total stations measure 3D positions. And what this means is that as your robot traverses the inside of the tank floor, it will also measure the robot's elevation relative to previous locations the robot has traversed. And what this means is you can additionally use an RTS to measure a contour of your tank floor to detect warping or settlements, which is a nice bonus and information that may not be captured at all with other types of localization for tank floor inspections. So this is a scenario where an RTS can really provide a lot of value. A scenario where this is not true is the case of an external piping inspection. If you think about the geometry of a pipe, there is no single location where an RTS will have line of sight to all sides. And this is okay. You can move the RTS through a process called resectioning to view a different angle of the pipe, but this is time consuming, disrupts the flow of the inspection. And additionally, piping generally has a lot of support structures and other systems going on around, meaning there could be a lot of obstructions for the RTS operator to drive around. An alternate option here would be a light-based metrology type system. Because you can provide multiple light-based metrology deployments in the environment, you could put them, say, on both sides of the pipe to ensure complete coverage at the first setup of your inspection, and you won't need to change it again as you proceed. Now, let's take the case of this specific pipe you see here in this environment. There may not be an elevated position for you to place a light-based metrology emitter above it to paint the top side of the surface with that laser light. This is a case where it appears there are no other tall buildings around. So in that case, GNSS may work for you for the top side of the pipe. And this is all right because sensor fusion systems are capable of fusing any set of sensors. So for this particular type of external pipe inspection, a good solution may be a combination of GNSS as well as light-based metrology systems. And there are many other assets we could go into. So at this point, feel free to ask any questions about assets or other things we've discussed here. And thank you for listening.
Awesome. Thanks, Thomas. So let's get started with some questions from the attendees. Just as a reminder, if you do have a question after watching the presentation, feel free to send it through the Q&A feature located at the bottom of your Zoom screen. Just to kick us off, there is a question specific to one of the use cases you had around tank floors. So for a tank floor, what is the horizontal field of view when positioned in the manway?
So it depends on the specific geometry of the tank in the manway. For instance, if the manway is recessed or you cannot deploy the RTS inside of the manway, you may lose field of view to some of the wings of the tank, the sections at an oblique angle and closest to the RTS system. You may lose field of view there in certain areas. And of course, if there are features inside the tank, such as piping, those could block your field of view. In those cases, you would have to rely on the other sensors, such as the onboard sensors like the wheel odometer and the IMU, to maintain good localization knowledge as you traverse the asset.
Awesome. And so do any of these solutions work for submersible robots?
That's an interesting question. Water is very good at attenuating electromagnetic radiation. So the systems that rely on that, like GNSS, the RTS, and light-based metrology, all probably wouldn't work very well. For underwater robotics, you can use sound-based systems. So that's where sonar comes from. Although Gecko doesn't deal with underwater robotic systems, at least not yet.
Awesome. So is there a way to synthetically pass GNSS into a tank floor space, essentially making the wall invisible?
There are a few approaches to indoor GPS repeaters. Some of them are very simple. They only reduce the time to first fix and don't provide accurate location information inside of a space. There are attempts to produce constellations knowing the geometry of the external GPS antennas and the internal repeaters. Those generally lose precision compared to external GPS. And that's also driven by the fact that GNSS is fundamentally radio-based. So if you try to repeat it indoors, you'll run into the same problems you run with other generic radio-based systems, which is that you'll get interference from just the characteristics of the environment, the concrete, the metal, and that can also harm your accuracy.
Gotcha. So do you use any software simulation tools for inspection?
Software simulation tools. We will use a suite of software tools in-house to replicate and evaluate our performance. But in robotics, there is a problem called the simulation reality gap, which essentially encompasses the difficulty of replicating physical environments with such fidelity that you can mirror the performance in simulation, which is actually similar to the problem of digital twinning I mentioned at the start of this presentation. So we generally don't because the value is unproven. We can test in the real world.
Gotcha. So this sounds like it might be more of like a European code, but somebody has a question around how do you deal with the ATEX and NEC restrictions required for design of these systems?
ATEX and NEC. I'm not familiar with these acronyms. Please do feel free to define them. I might know the full spelling there, but I'm not familiar with these restrictions, and I could get back to you on that.
Sure. And so their other question was, do you need to remove sludge from tanks? And if so, are you in need of this service prior to the inspection?
Generally, yes. We use, in the case of ultrasonics, we will use water as a couplant. And in that case, we do need the tank to be empty. Additionally, our robots are not explosion proof. So if there's any petroleum products in there, those things would have to be removed before an inspection by Gecko takes place. Although the technology I've discussed here is company agnostic, this is an overview based on research papers and literature review to just the types of technologies that can be deployed by anyone to perform these types of inspections.
So what current localization methods do Gecko robots currently use?
That depends. It's hard to answer generally because it depends on the type of asset that's being inspected and also the accuracy requirements. I mean, one of the reasons that I know as much as I do about these technologies is because Gecko has, at the very least, experimented with all the ones that I've discussed here today. So for any specific inspection, it would simply depend on the requirements and what our client needs.
Great. So were there any that seemed really good in theory, but then didn't really work well in practice?
That's a good question. You'll run into a lot of surprising problems that you wouldn't expect. Again, because of the types of environments our robots navigate in. For instance, the IMUs that come with the inertial measurement units that come with compasses, these are often really helpful for, say, airborne robotics or self-driving cars. The trouble is, in a lot of these environments, there are ferrous materials and magnets nearby, and those will disrupt the compasses. Similarly, with the case of, say, a RTS system, they are weather hardened, but simply because of all of these structures that take place in, say a refinery or a power plant versus an outdoor environment where a land surveyor might use them, like in a field or in a construction site, you will run into a lot more manual operation of the RTS than a surveyor might.
How many locations per second are calculated for the robotic systems that Gecko uses?
That's an interesting question, actually. A lot of these surveyors will take measurements at different speeds. A lot of these sensors, I mean. For instance, there are some inertial measurement units that can report their calculations at thousands of times a second. On the other hand, systems like GNSS or robotic total stations, they'll usually only measure at about 1 sample per second. So it's variable. And that also changes once we use sensor fusion techniques, and that depends on the technique. So that's time resolution. Now, the differences for positional resolution for localization, if we need better requirements than, say, a sensor can provide, you can simply drive your robot slower to increase your resolution or your density. But of course, the trade-off there is increased inspection time.
Gotcha. So how does RTS get its own control point location?
Yeah, I guess I should have mentioned that. RTSs, they have a few different types of lasers, and one of them is called, well, I guess it depends. Essentially, the way the RTS measures its own location is it measures a control point with its rangefinder and with its rotation axes, and then it knows its own position. So then any subsequent measurements taken by the RTS will then be calculated relative to that control point. And additionally, RTSs can be referenced against multiple control points at once. There is a setup procedure that ensures you do have a reference for all measurements you take.
Great. So for your LBM slide, does the item or thing that you're looking at need reflectors?
There are optical components inside the emitter, the LightBased Metrology base station. You don't need reflectors in the receiver. The receiver are just photodiodes that are tuned to the laser wavelength. The only setups you need in the environments for LightBased Metrology to operate are those base stations.
And what is a typical control point on a pressure vessel?
It would probably depend on the type of vessel. You can use existing features such as inlets or outlets, existing weld lines, or manways, for instance. Basically, anything that be useful for multiple. Or you could also introduce leave behinds into the environment if it is an acceptable solution.
And then how precise is a localization type that Gecko uses as far as reproducible data?
Hmm. So from a reproducibility perspective, we use, say, the same control points or the same features in the environment. And that is how we ensure our reproducibility across many types of assets. It's hard to say generally because, again, it does depend on customer requirements. Even for the same type of asset, different customers may require different accuracy metrics. And so this is hard to say generally. Again, it will also depend on the tools we need or the tools we use.
Great. And then Stephen just came back and mentioned that the ATEX and NEC is essentially the certifications needed to enter oil and gas facilities. So they're wondering if, can our inspection equipment be attached to other operating systems for use submerged in oil and petroleum?
Up a little there. Could you repeat that?
Yeah, sorry. So the ATEX and the NEC restrictions, they're basically certifications needed to enter oil and gas facilities. So they're wondering if our inspection equipment can be attached to other operating systems for use submerged in oil and petroleum.
I actually don't know the answer to that. Our systems are quite modular, have many components. And we have done work at oil and gas sites, different subsystems. I wouldn't be the person who knows that, but I can find you.
I could chime in here real quick. Our development has really been focused on providing robotic tools in situations where human access is the norm, and that level of preparation is the expectation. So we're typically working under a hot work permit, and we're going into otherwise safe environments. But that is just where we are in our current development phase. So hopefully we'll have future follow-ups should we develop in those directions.
You can call me when that happens.
There we go.
Awesome. So those seem to be all the questions we have currently. Thanks everybody for joining us today. We will be sending out the recording to this webinar to everyone so that you can either rewatch or share it with your colleagues. Otherwise, thanks again, Thomas, for this, and everybody have a great holiday weekend.